Right. Okay. All right. So I hope I'm audible. All right. Right. So good evening. Let me check whether I'm audible. Okay, right. All right. Good evening again. We'll start. So today we are the day 5 of H2A, and I have allocated today's discussion for surface tension. Right. Since we have finished our finished in our classes in the sense in the reverse class we have finished surface tension and viscosity, no? Right. So that's why I have allocated this session for surface tension, and in coming weeks I'll be allocating sessions on viscosity, elasticity, and other lessons we are covering there as well. Right. All right. So today will be the first day of surface tension. So most probably you will be having another day, second day for surface tension as well, with the number of questions we have to discuss. Right. So today this will be the first day of surface tension. All right. Then we are 25 weeks ahead of the exam. Right. Exactly 25 weeks and 2 days. Right. Today is Friday. Friday is also already gone now. Right. It's 8 p.m. now. Right. So yeah, 25 weeks and 2 days ahead of the exam. Right. Okay. So get the maximum benefit from these discussions also, and utilize your time, full time for academics, and you are also starting your vacation, kind of a small vacation due to O levels today onwards, no? Right. So utilize your vacation also to the fullest. Right. Utilize your vacation also to the fullest during the time, because now usually you might be free in morning hours, right? If you are attending school the other days, right, you should be free, you might be free during morning hours, no? So without sleeping like 10-11 p.m 10-11 a.m in the morning, right, 10-11 in the morning, so you can wake up at the usual time, right? If you are going to school, you might be waking up around 5:36, something like that, no? Right? So you can keep waking up during the same time, and utilize your time for academics, only for academics, right? Just 25 weeks. Okay. So without further ado, let's go to the discussion. If you haven't downloaded the paper in the sense questions, sorry, from the paper questions, you can go to either WhatsApp or Telegram channels and get it downloaded, right? So I think I have shared it in the groups as well, in some of the groups, right? In 26 groups I have shared, right? And if you are here, you can go to the description of the video, right? You can go to the description of this YouTube video, and from there also you can download it, right? If you need these questions, these are the WhatsApp questions, right? And let me put the link to the chat as well, right? Then if there's anyone who don't have the questions with you, you can still get it, no? Give me 1 second. I will put this link to the YouTube chat as well. Right, I have put a pinned message. Right, I have put a pinned message in the chat, in the live chat. So from there also, if needed, you can visit there and download the paper, download the questions from the paper. Right, let's do it. Right. Okay. So let's go to the discussion without further ado. Let me share my screen. Okay, my screen is visible, right? Okay, visible now? Right, let's start. First one. On Earth, a liquid rises to a height h. The space is not given h above the level of the liquid in the container when placed in a capillary tube. Right. Rises means this is about a what? We discussed this. As capillary rise and capillary depression. Right. So this is about a capillary rise. Right. So first thing is, now this is about a capillary rise. This is about a capillary rise. Right. This is about a capillary rise. Right. For capillary rise, we have proved two equations. If the tubes are well cleaned, capillary rise is H rho G is 2T over R. And if tubes are not well cleaned, right, capillary rise is H rho G equals, I'm just recalling the theory part, right, 2T over capital R cos theta, right, where simple R is radius of meniscus, and capital R is radius of tube. Right? How many equations do you prove? These are the equations we have proved. Radius of meniscus and radius of tube. Right. So what's given is on a container when placed in a capillary tube. This experimental setup is taken to another planet where the acceleration due to gravity is 2/3 of that on Earth. Acceleration due to gravity is 2/3 of that of Earth. Then if acceleration due to gravity is g on Earth, right, on that particular planet it should be 2/3 means 2g over 3. Something like this, right? And the atmospheric pressure is half of that on Earth. I'm not interested about atmospheric pressure because pressure is not a variable in these equations. Pressure is not a variable, so I'm not interested. Right? What will be the new height of the liquid column in the capillary tube? New height. Okay. If angle of contact is not given, which means by default we won't be considering angle of contact. Right? So by default scenario is they are well cleaned. By default scenario is they are well cleaned. Right? We have discussed. Then let's go with this equation. Right. See, on Earth. So first one, we can apply this on Earth. No, you can apply this on Earth. On Earth, H rho G equals 2D over R. Right? H rho G equals 2D over R. Then on that planet, right? Say H is H dash, the new value, right? Rho is same because same liquid, and G is different. G is 2G over 3 there, right? Same surface tension because same liquid, and same radius of tube because, sorry, same radius of meniscus because same tube is taken. We know under this scenario, right? Under this scenario, if well cleaned, if this is well cleaned, we know that radius of tube and radius of meniscus are equal, no? Right? So you have to know those things. Radius of tube and radius of meniscus are equal. So in that case, if the same tube, same setup is used, same experimental setup is taken. Same setup means same tube. So therefore, same radius remains. So we got two equations. See, first one, right? Second one. So you can either give a substitution or you can divide. Let me substitute. Now for 2T over R, I can substitute H dash rho 2G over 3 from second equation. Then rho to G cancels. We need H dash. H dash is 3HO2. Right? So that is in first answer. 3HO2. Right? See how these proved equations are used? That's a proved equation. Right? So take down quickly, if anything. That's a proved equation. And for capillary depression also we have proved another 2 equations, right? Okkama equations 4 prove කරානේ. There were 4 equations we have proved for capillary rise and capillary depression, right? Directly you can get the equation, you can use the equation here. That's a direct application of the equation, right? Let's move on. Right. In which of the following vessels does the liquid surface remain flat? Remain flat right up to the walls when it is filled with any liquid to a certain height. When it is filled with any liquid to a certain height. The height to which the liquid rises depends on the nature of the liquid used. Nature of the liquid used. The height to which the liquid rises depends on the nature of the liquid used. Okay. Okay, now we know if this is put onto a container. If this is put onto a container, if the liquid is put onto a container, if there is a wetting liquid, wetting means spreading liquid. If there is a spreading liquid, this is how this surface will be. No, this is how the surface will be. See, with small angles of contact like this, right? So these two places are the places where the angle of contact occurs. Then simply that is a liquid meniscus, right? That's a liquid meniscus because wherever a liquid is curved, that is a meniscus, right? So wherever we have a curved liquid surface, that is a meniscus, right? Now, if we just try to plot these liquid surfaces, right? So here it will be something like this, and here it is going to be something like this, and here on this one it is going to be something like this, right? And this one something like this one also something like this, right? Now, we know at here we have angles of contact. At these points, we have angles of contacts, right? Angle of contact. And about a spherical shape, right? About a spherical shape, we know something from refraction, right? About a spherical shape, we know something from refraction. That is, when light rays are fallen perpendicular to the surface, it won't be refracted. No? When light rays are fallen perpendicular to the surface, it won't be refracted, right? That is also one thing that is discussed under optics. That is something discussed under optics. So when we are looking at the surface here, right, we will through that through refraction as well. So I'm going to check on two things. One is angle of contact and the other thing is about refraction, right? So let's check on both of the things. See, here now when we come up, when this surface is getting narrowed, surface in the sense when the area is narrowed, always meniscus, curvature of meniscus increases. Now in this case, R decreases. R decreasing means curvature of the meniscus increases. So it won't be flat, right? Right? It won't be flat always. And in this case, the opposite happens. In this case, opposite happens, right? Always R increases. When R increases, curvature or the meniscus increases. Meniscus increases means it is going to go towards the flat side, right? But not always flat. Right? And let's keep 3 and 4 aside a bit because they are curved surfaces, and let's go to fifth one. Now in fifth one also, when this changes, right, in these narrow sides of the tube, narrow parts of the tube, radius decreases. When radius decreases, curvature increases, so it won't be flat. Now I have that I between these two curved cases, curved cases, right? So in a curve we know now even though we go up, that impact is not that high. The impact is not that high. That impact of narrowing it down is not that high, right? And compared to the third one in fourth case, the narrowing is higher. Getting narrowing is higher. Getting narrowing is higher means radius decreases. So we know curvature is going to increase. Curvature increases. Now in this case also, curvature is going to increase, trying to increase, right? But compared to this one, when we go up, when this angle decreases, to keep the same angle of contact, to keep the same angle of contact, this liquid is going to spread out, something like this. Now, if the angle of contact is, let's say, 30 degrees, if there is 30, it should be 30 at any level, no? Likewise, It should be 30 at any level now. 30 තියාගන්නවා. When it is trying to keep 30, can you see that it is going to be more towards the flatter side? More towards the flatter side. Almost flat. So we can consider this as flat compared to the fourth one, right? So therefore, final answer is 3. And about the refraction also, when light rays fall onto this surface perpendicularly, there is no refraction. Since there is no refraction, right, we don't see that meniscus that much as well. Reasons dekama balanda, you can check both reasons. So final answer and the best answer that we can go ahead with is 3. Right? That's kind of a special question, special and a unique type of a question. And after 93, there won't be any questions came from that type as well. ඒකත් මතක තියාගන්න. හරි? මේ වගේ එකක් ආවේ නැහැ. පොඩක් ආගියු කරපු විදිය බලන්න. Right? 3. These variations we have done, we have plotted in the class, right? Okay, so we know here we have a liquid meniscus this side, we have a liquid meniscus here to this side, right? And the theory part is, this respective theory part is, if you jump into a liquid meniscus, pressure increases by plus 2 DOR, right? And if you jump out from a meniscus, pressure decreases by minus 2 DOR. And if you have soap, right? If you have soap, right? For soap, you have to use 2T instead of T, right? So these are the theory parts. Now let's start writing pressures. Okay, starting from here. Look at here. This is open to atmosphere, no? P0. Right? Start from that point, P0. That is open to atmosphere, P0. And here you are jumping out from a meniscus, right? You are jumping out from the first meniscus, then minus 2 DOR, right? Minus 2 DOR. Then jumping out, pressure decreases. At once, pressure should be decreased, right? At once. Then 3 is not going to satisfy our conditions. Again, decrease. Others are fine. And from here to here, we are coming down through a liquid. We are coming down through a liquid, through the liquid, right? Coming down through the liquid is HROG part, right? So when you plot HROG, we know delta P equals HROG. When you plot HROG with height, this is a constant, no? This is a variable part. This is constant, gradient. And this is our y. So it is going to follow y equals mx. Graph is linear, right? Graph is linear. And at this point, you are jumping into a meniscus again. Jumping in means pressure increases again, right? Pressure increases. Increasing part fall, that is wrong, right? Pressure increase when down. And you have to check to which level pressure is going to increase, whether it's going to come to the atmospheric pressure again, or it is lower than atmospheric pressure or greater than atmospheric pressure, right? Now this is also meniscus. Atmosphere is here. This is also meniscus, which means pressure inside this thing is P0 plus something, no? Because there is a meniscus. P0 plus something. Then this should increase up to a level which is greater than, which is above the atmospheric level. It should be above atmospheric level. Then 1 is wrong. Atmospheric level eකට වඩා වැඩි වෙන්න බෑ. Right? And 5 is also wrong. See, only answer remains is 2. This pressure inside should be, this should be inside pressure. Pressure inside is, this is greater than P0. That is greater than P0. Right? Answer 2. So we discussed like quite a few questions from these types in the class, right? Variations, pressure variations, horizontal ones, vertical ones, everything, right? Now these are vertical ones. 4. In the equation given below, V represents velocity, gamma represents surface tension, and rho represents density. The constant A has the dimensions of. Now there is a dimensional question, dimensions question, right? But since it is from surface tension, I have put the question here. I have means in the classification also, the question is usually here, right? That's why. Otherwise, these are units and dimensions actually, right? So we know if this is an equation, right? Dimensions of left hand side and right hand side should be equal. And if there are terms added, right? If there are terms added, dimensions of these added terms should also be equal, right? Then we can say dimensionally these three are equal. Dimensionally these three are equal, right? Then you can go with any of the terms here, right? Let me go with this v squared and this one. I'm going to consider these two. V squared, v is a velocity that was given. Velocity is dimensions of velocity, LT minus 1, whole thing squared, right? 2 phi is dimensionless, no? Keep it aside, 2 phi is dimensionless. Gamma is surface tension. What is the dimension of surface tension? We have proved mt minus 2, no? Right? මතක නැත්තයි හදලා ගන්න. F equals TL. F is mlt minus 2, right? T into T can dimensions of T. L is L. See? So dimensions of surface tension is mt minus 2 if you can't remember. Then this is mt minus 2 over rho is given density. Density එක දන්නේ නැත්නම් ඒකත් හදලා ගන්න. Density is MOV. So that is ml minus 3 as the dimension. Then ml minus 3 dimensions of A. Right? Simplify. M to M cancels. Right? And once you simplify this side, L squared T minus 2 comes. And here T minus 2 is there. And when L comes to the top, L cube dimensions of A. Right? See what cancels? T minus 2 to T minus 2 cancels. L squared to L cube cancels. Then dimensions of A remains as cross multiply L. Right? L. That's a small question. That's a easy one. Easy and a small one. Right? Right? Let's move on. Feel free to ask if anything. YouTube has two limbs made of capillary tubes with internal radii R1 and R2. R1 greater than R2. Right? The tube is held vertically and filled with water as shown in the figure. Right? If rho is the density of water and gamma is surface tension, the difference in the water levels H is given by. Okay. Now, what I can notice is both sides are open to atmosphere. Both sides are open to atmosphere. Since both sides are open to atmosphere, we can start writing pressures from one end and you can reach the other known point. Other known point means again atmosphere, right? So let's jump into this from the atmosphere side, right? Start from the left end, left limb, P naught, right? Now here curvature is not properly given, but we have to know that is it given as water? Water, since there is water, we know the curvature is going to be like this. See, curvatures are going to be like this, right? Water is a non-liquid. Water is a non-liquid. That we have to have some idea. Right? Then start from here. These are the menisci now, right? P naught jumping out from the first meniscus here, jumping out. Then minus 2t over R1, minus 2t over R1, right? And since this is a same static liquid, same level pressures are equal. Then this pressure is equal to the pressure here. When you go up, minus H rho G, and here again jumping into a meniscus plus 2t over R2, right? 2t over R2 equals, now we are in the atmosphere again, P naught, right? And T is given as sigma, no? Right? T is given as sigma. Sorry, T is given as gamma. Let me plug those values here. P naught to P naught cancels now anyway, right? And I'm subjecting H because we need H. H rho G equals T is given as gamma, no? Then we can see 2T is common, which means 2 gamma is common. 2 gamma is common. Then 1 over R2 minus 1 over R1 remains this side. Subject H. So H is given by 2 gamma over rho G times 1 over R2 minus 1 over R1. 2 gamma rho G 1 over R2 minus 1 over R1. This one. Right? Just write down pressures. Right? Starting from a known point. If you write pressures to another known point, always we can get an equation. If you start writing pressures from a known point and finish writing pressures from a known point, always we can get an equation. Right? Take down if anything. Right? We discuss such scenarios. 6. A soap bubble has a radius of 3 centimeters. If the surface tension of soap solution is 1.5 times 10 to the minus 2, the excess pressure inside the bubble is. That's a proved equation, right? Excess pressure inside the bubble is, right? Excess pressure is a proved equation. Delta P equals, right, 40 over for a soap bubble. Because we are using 2D instead of T for soap, no? Right? 40 over for a soap bubble. Just a plug and play, right? 4 times T 1.5 times 10 to the minus 2, right, over R 3 centimeters. 3 centimeters 10 to the minus 2, right? Simplify. That's it. 1.5 times 2 here, then 2 times 2 here, then 2. These 2 also cancels, no? 2 excess pressure Nm minus 2. See how easy this question is, right? Surface tension MCQ is a definite MCQ you are getting in the exam, right? A definite one. Definite one. Right? Surface tension, 1 MCQ, viscosity, 1 MCQ, elasticity, 1 MCQ, right? Definite ones, right? Simple one. Let's move on. 7. The capillary rise of water in metallic capillary tube of internal radius capital R, right? Radius of tube is found to be equal to that in a glass capillary tube of internal radius simple R. The angle of contact between water and glass is 0. If the angle of contact between water and the metal is, right. Now for capillary rise, we know without angle of contact, H rho G equals 2T over R, right? Now, okay, the 0 found to be equal to, right, if the angle of contact between wood and glass is 0, then let's apply this for glass without angle of contact, for glass, right? H rho G equals 2D over R, and glass tube का capital R simple R, the capital rise of a metallic capillary tube simple R, equal to that tube in internal radius. Okay, glass is simple R, no? Then for glass, this equation is just as this is, just as this, H rho G equals 2D over R. Then for metal, let's apply for metal again. That is with the angle of contact, then H rho G equals, right? H rho G equals, it says H is equal, the capillary rise is equal in these two cases, same H, and since there is the same liquid, rho is same, G is same, both are on earth, and same liquid, 2D, right? And here radius of tube comes into angle of cos theta, the angle of contact cos theta, right? These two are two proved equations, right? Without angle of contact 2T over R, with angle of contact 2T over capital R cos theta, right? Now since left hand sides are equal, we can equate both sides, no? Right? So let's say 1 and 2, 1 equals 2. That's it, 1 equals 2. Then 2T over simple R equals 2T over capital R cos theta. 2D to 2D cancels, right? We need cos theta, we need theta actually. Subject cos theta is capital R over simple R. So theta equals cos inverse capital R over simple R. Cos inverse capital R over simple R 3. Easy, yeah? As long as you know these equations, right? Very much easy. Equations ටික තමයි ඉතින් දැනගෙන ඉන්න ඕනේ. As long as you know the equations, that is very much easy. Right? Let's move on. 8. A capillary tube is gently dipped vertically into a liquid as shown in the figure. Which of the following graphs best represents the variation of cos theta with the height h? Cos theta with the height h, right? Then that is about a capillary rise, no? So start from capillary rise. The equation of capillary rise is H rho G equals 2T over R cos theta, where this capital R is radius of tube. This is radius of tube, right? Now we can identify these variables. See, we can identify these variables like this. Now you are going to plot the graph between cos theta and h no. Cos theta and h no, right? Then subject cos theta and take it to our dependent axis, right? Then cos theta equals, keep h aside because we are going to plot this with h, right? Then our rho g capital R over 2t. Let's isolate it and h. Now identify our variables. This is x, right? This part is a constant. This whole part is going to be the gradient, and this whole term is y. Then it is going to follow y equals mx. Very straightforward. Then 2 is wrong, 3 is wrong, 4 is for now fine, 5 is also wrong because y equals mx. Y equals mx should be a straight line goes to origin. Y equals mx is a straight line goes to origin. Right, now let's argue what's happening hereafter. Now when this is dipped, right? Dip karna tube is gently dipped, right? When this is dimmed, right? When this is dipped, at some point it is going to reach the top of the tube, no? Once the top of the tube is reached, right? Once the top of the tube is reached, then there won't be any angle of contact when the liquid reaches this point, isn't it? There won't be any angle of contact when the liquid reaches this point. Angle of contact becomes 0 at that point, right? Cos 0. Cos 0 is 1, which means after this point, it is going to be constant, right? It is going to be constant. Then the obvious pick is 1. Obvious pick is 1 because after this top point, I mean top end, after the top end of the tube, the angle of contact is no more. No meniscus. No meniscus. Simple as that. No meniscus after that point. Meniscus එකක් නැත්නම් ඉතින් angle of contact එකක් නැහැ. Right? So basically what I have used is this, our basic approach when plotting a graph, right? Our basic approach when plotting a graph, right? Starting from the known equation, and we have to model, you have to arrange the terms, model the terms as we are getting a standard curve. So we got a standard curve, y equals mx, right? Next, two soap bubbles of radii 3 centimeters and 4 centimeters coalesce in vacuum under isothermal conditions. Isothermal means temperature is constant. Isothermal, constant temperature. Isothermal again, constant temperature, right? The radius of resulting bubble is, right? Two soap bubbles of radii 3 and 4 are okay, and it is going to form another bubble, something like this. There are two bubbles, right? I discussed this same question, same in the sense, same type of a question in the class, right? This is 3 centimeters and this radius is 4 centimeters. These two are going to coalesce together and going to form a single one like this. Let's say radius of that one is r, right? Since volumes cannot be equated because they are bubbles, right? Inside the bubble, what we have is air. So volume is equal to then apply conservation of energy, right? Using conservation of energy. Using conservation of energy, right? Total initial energy. We know energy of a soap bubble is, this is a proved equation. Energy of a soap bubble is 8.5 r squared t. Energy of a soap bubble of radius r is 8.5 r squared t. We have proved in the theory, right? Then for first one, it should be 8.5 r1 and r squared and 3 squared, right? T plus for the second one 8.5 4 squared t, and for the new one 8.5 r squared t. 8.5 cancels, right? T cancels. Then 3 squared plus 4 squared equals r squared. 9 plus 16 equals r squared. R squared equals 25. R equals 5 centimeters. Right? Simple. Comparatively, surface tension questions are easier. Right? Comparatively. Typically, surface tension questions are easier. That's an easier types of questions we have. Right? Miss karaganne epa me lakunu. These are like very much gettable marks. Very much gettable. Miss karagattොත් අපරාධයි. They are very much gettable marks. Very much gettable. Mechanics more lazy, right? Compared to lessons like mechanics, waves, right? Basically, properties of matter is a comparatively easier unit, right? So that's one of the reasons I started that earlier, a little bit earlier in the reverse class, because to you to familiar with these questions more before the exam, then you can easily tackle the question in the exam. Right? You are getting an essay as well. Then a vertical capillary tube is partially immersed in water. Air is pumped into the tube so that the pressure inside it gradually increased. The lower end of the tube is at a depth of h below the water surface. Right. As h is varied, which of the following graphs best represents the variation of the maximum pressure P that can exist inside the tube with h? Okay. Now something like this, ne? In this one, this tube is dipped. Tube is dipped. Right? A tube is dipped inside this. And the lower end of the tube is at a depth h below the water surface. Right. So let's assume somewhere here we have a meniscus like this, right? And this depth is h. Right? We can write something for this pressure inside, no? That is not rho. Rho the diya. Oh, wait. Which of the following graphs best represents the variation of maximum pressure? Right? It should be P, not rho. It should be P. Right? Should be P. Right. Let's see. Then here, since it is open, P naught, no? P naught tax. P naught tax. And pressure inside is P. Right? Start from here and start writing pressures. P naught. We are going in plus H rho G. Right? Plus H rho G. Going in plus H rho G and jumping out from the meniscus minus 2T over R equals, now we add P. Right? Now we add P. Now we add P. Right. Then let's model this equation. P equals rho G. Let's keep H aside. Right? Plus P naught minus 2T over R. Now we can identify these variables. Right? H is my x variable. Whatever it is as a product with x is gradient. Right? T is my y variable. Right? And this whole part is intercept. So we are going to get a mx plus c. Only mx plus c graph given here is 3. Answer is 3. Right? See, graph plotting. Right? I have used graph plotting techniques. Graph plotting techniques. They are common. They are common everywhere. Right? Now it's been, I think, around an year since I have conducted the graph plotting session for 26 batch. Right? And sooner for 27 batch also I'm going to have the graph plotting session, right? So still, if there's anyone who didn't get it, right, who are not comfortable with plotting graphs, right, you can get the updates through channels. So when the session is going to be held, you can get the updates and join the graph plotting session if needed. And the last year graph plotting session is still on my YouTube channel, right? You can go watch there if needed. Right? 11. One limb of a glass tube is a capillary tube, while the other limb is a wider tube. Right? Capillary. Capillary. The narrow one. And this one is a wide tube, wider one. Right? Capillary and the wider tube. As shown in the figure, when water is poured into the U-tube, the equilibrium heights of the water columns in the capillary and the wider tube measured from the common level O dash are H and H respectively. Right. Now, first of all, you should have this idea. Capillary rise is H rho G over, H rho G equals 2T over R. No? When radius decreases, when radius decreases, H increases. Then lesser the radius of the tube, higher the H, which means for sure I can say, right, compared to this side, liquid level at this level, this height, this side, this limb has to be higher, right? That is simple H neither. Simple H and capital H. Then for sure this simple H is higher than this capital H because of this reason. Then always simple H should be something greater than capital H. Always there is going to be something greater than capital H. Right? කෙලිමම මේ equation එක ගත්තේ. හරිනේ? Equations ඉතින් මතක තියෙන්න වෙනවා. හරිනේ? So at any given point, at any given time, simple H should be greater than capital H. Simple H should be greater than capital H. Right? ඕන හිතලා ගන්නත් පුළුවන්. Simple H should be greater than capital H. Right? So if it is like this, capital H and simple H are equal, no? If simple H is greater, right? If simple H is greater, it should be a value like this, a graph like this, first one, right? It should be like this, first one. See, should be like this. ඕනනම් 0 කියන point එක ගන්න පුළුවන්. At this minimum level, when this is reaching 0 also, even if H dash is, capital H is 0, even if capital H is 0, simple H won't be 0, right? Right? When capital H equals 0 also, simple H is not going to be 0 because simple H is always greater than capital H. Simple H is always greater than capital H. මම එක මෙතනින් ගත්තේ. Right? Simple H is greater than capital H. Right? එහෙනම් 0 කියන point එක check කරලා අහු වෙනවා. When H is 0, H should be non-zero. Right? So answer is 1. See how easy the question is if you know these theories properly. Right? They are not far questions. 2000. Right? Next. So you have to know equations. That's a basic here. Knowing equations means that's a basic requirement. Right? Fundamental requirement. Knowing the equation is a fundamental requirement. Right. Next. 12. A steel razor blade can be made to float on the surface of water. Consider the following statements. Right, I think I discussed about that scenario in the theories as well. Floating small metal pieces, metal objects in water surfaces, on water surfaces, we discussed, right? Okay, the floating of the steel razor blade contradicts Archimedes' principle because no upthrust acts on the blade. It is true that no upthrust acts on the blade, but it doesn't contradict. The reason is when this happens, this blade is not immersed. The blade is not immersed, right? Since the blade is not immersed, right? According to U equals V rho G, there's no immersed volume, right? V equals 0. Since V equals 0, U equals 0. That doesn't contradict, right? That follows that follows Archimedes' law. That follows. So that doesn't contradict, right? Contradict that doesn't contradict. It follows. So this is wrong. That doesn't contradict. It is 0 because V is 0. It is 0 because V is 0. No immersed volume. This is just floating on the surface. Without any immersed volume. With 0 immersed volume. Simple as that. B. The steel razor blade is supported on the water surface by forces due to surface tension on water. Exactly correct. Right? So there will be forces due to surface tension acting throughout this one like this. Right? There will be forces due to surface tension acting throughout this one like this. Right? And the resultant acts like this. And that is counterbalancing this weight W and mg. Right? It is counterbalancing the weight. That is what happens. That is correct. Right? Exactly correct. B. C. Adding soap to water causes the steel razor blade to sink because soap reduces the surface tension of water. Exactly, yes. Keep that in mind. What is happening is, right, keep the reason in mind. We know, if you are doing chemistry, definitely you know, right? We know there is a strong hydrogen bond between water and water. No? There's a small hydrogen bond between water and water. When soap is added, the strength of that hydrogen bond decreases. When that decreases, surface tension of water decreases when soap is added. Right? Keep that in mind. Keep this in mind. Important. You better take this down. Surface tension of water decreases decreases when soap is mixed. When soap is mixed, right? So which means it is going to spread more, right? Surface tension decreases means that is going to spread more because bonds between water and water molecules decreases, right? හරියටම කිව්වොත් which force? Cohesive force. හරියටම කිව්වොත් cohesive force between water and water decreases. Cohesive force between water and water decreases due to soap because it loosens the strength of the hydrogen bond, right? So when that decreases, yeah, this is correct. This is also correct. So correct answer is B and C, right? So about this soap thing, if you didn't know, you better take it down because that's something we have to know. And regularly and very frequently, we are getting questions from soap. Soap and water are the most popular liquids we have. No, that's why. So therefore, from soap and water, always questions are coming. Most popular two liquids are water and soap, and the third one is mercury. ඔය තුන තමයි ඉතින් හොඳම liquids උනා. හොඳම in the sense the most frequent liquids, right? Most frequently coming liquids, right? And I think you have already seen in the channels, we are going to have our optical instruments seminar on this Sunday, right? We are going to have optical instruments seminar on Sunday. Optical instruments seminar on Sunday 15th. Sunday 15th, Sunday at 7 p.m. right? 15th Sunday at 7 p.m. You can get all updates to the channels right, at 7 p.m. and this will cover all the theories from scratch, right? This will cover all theories from scratch. This is the plan. This will cover all theories from scratch, from zero, right? Plus question discussion. Question means a past paper discussion from optical instruments, and I need to finish this part entirely, and question discussion, right? This will be happening, and I will be physically at Lisa, right? Physically at Lisa, so you can come to the institute if you are joining physically, right? You can come to the institute if you are joining physically, right? Physically at Lisa, right? Lisa Horana, and online, Islandwide online on YouTube, right? So that will be happening on this Sunday, right? I just remembered because if there's anyone who need to join, if you haven't seen, haven't got the updates yet, right? You can get ready, and this session will go up to like 1 a.m. in the morning, right? Like 12:31 in the morning, right? Something like that. And just by that single seminar, I'll be finishing all the things about optical instruments with followed by a question discussion, right? Okay, no any registrations required, right? No any registrations required. Tute is also given for all of you, right? If you are coming physically, you can get the hard copy from the institute, right? So if you are joining online, you can get the soft copy from my soft copies, right? You can get the soft copy. No any registration, whether you are coming physical or online, that doesn't matter, right? That's it. Okay, so let's proceed. Right. Two soap bubbles coalesce. After joining, the radii of two bubbles are A and B. After joining, radii of two bubbles are A and B. A greater than B, the radius of curvature of the interface separating two bubbles is, right? Now, this is not forming a whole new bubble, right? But rather, this is about two soap bubbles, right? That you need to understand. So the scenario is something like this. That scenario is something like this. Two soap bubbles are coalesce like this, something like this. And මෙන්න මේ වගේ scenario එකක් දැන් තියෙන්නේ. Two soap bubbles are coalesce like this, right? And the radius of this one is given as A. No, A is greater, ne? A is greater. So radius of the other one is given as A. Radius of this one is given as A. Radius of this one is given as, sorry, අනිත් පැත්ත. Radius of this one is given as B, right? And this is a different surface, right? Even though this looks same, radius of this surface is different. Huh? That's a common surface. Let's assume radius of that common surface as x. Right? Let's assume the radius of common surface as x. Right? I think we discussed the similar type of a question in the class. So we know this side is open to atmosphere, P naught. This side is also open to atmosphere. Then we can start writing pressures from one known point, and you can finish writing pressures from a known point again. If there are two known points of pressures, right, that is one of the basic things we do. One of our main approaches we take, right? Then start from here, P naught. You are jumping in, then plus 40. There are soap, no? Soap, ne? Soap. Plus 40 over B. Plus 40 over B. And here we are jumping out minus 40 over X. Minus 40 over X. Right? And here we are jumping out again minus 40 over A. Minus 40 over A. Right? Equals P naught again. Once we jump in, again we add the atmosphere, P naught again. Right? Then P naught to P naught cancels. Take this to the other side. Right? Take this to the other side. Then 40 over X equals 40 over B minus 40 over A. Right? 40 to 40 also cancels. Then 1 over B minus 1 over A equals 1 over X. 1 over B minus 1 over A equals 1 over X. Apply a common denominator. Apply a common denominator. That's it. Right? Let me do the rest here. Here, common denominator is BA. Right? And this is A minus B equals 1 over X. We need X. X equals BA means AB, no? AB over A minus B. AB over A minus B, answer 4. Right? First you have to understand that radius of the common surface is asked. Radius of the common surface is asked. Right? Give me 1 second. Radius of the common surface is asked. Otherwise, it is not going to form a whole new bubble again as before. That is not going to form a whole new bubble again as before. One second. Right? That's a common surface. Right? I did a question in the theory class from a common surface. Same thing. Same thing. Okay. Right. Next. 14. A six-legged insect stands on surface of water. The radius of each circular flat foot is 2 times 10 to the minus 4. Radius Radius of the foot is 2 times 10 to the minus 4 meters. Right? The surface tension of water is 7 times 10 to the power minus 2 Nm minus 1, right? The maximum weight of the insect that can be supported by water surface is, right? Now we know when this insect is on water surface, right? It is something like this. No, now this insect has 6 legs. 1, 2, 3, 4, 5, 6, something like this. And he is going to on a water surface like this. Right? Right. Then if force on one leg is F, right, altogether it creates a force of 6F, no? And we know mg is counterbalanced by these forces. So we can say, considering his equilibrium, right, using vertical equilibrium, vertically upwards forces equals vertically downwards forces. Vertically upwards then 6F, right, downwards mg, right, weight in the maximum weight. Okay, then we know force due to surface tension F equals TL. Right? If radius of foot is given, then we can write the circumference, because now if I show you a cross section of this, right, it says a circular foot, no? Then foot is like this, it's a circular one, right? Foot is like this, it's circular, and this radius is given. Contact in length is going to be the circumference, right? Contact in length is circumference, right? එහෙනම් අපි එකවර substitute කරමු. 6 into F is TL, right? ලියලා ඉන්නකො TL is mg, right? But L is 25R in this given scenario. L is 25R, right? Then 6 times T is given 7 times 10 to the minus 2, L 2, 5, pi is 22 over 7, R 2 times 10 to the minus 4, R 2 times 10 to the minus 4 equals mg. We asked about the weight, no? Then if this is simplified, that's it, right? See how it is going to simplify. Is there anything cancels? No, nothing. Then isolate the 10 to the powers and simplify. 7 cancels, only 7 cancels, right? That's it. Isolate 10 to the powers and simplify. 6 times 2 remains 12, 12 into 22, 12 into 2 and 24, 24 times 22 ki lagaknin, 24 times 22 remains, are 6 times 2 is 12 times 2 is 24, 24 times 22, 4 remains with 10 to the power minus 6, are equals mg. 24 times 22, what's the value, right? That you have to check. 24 times 22, 528, right? This is 528. So this is 528 times 10 to the power minus 6 equals mg, right? Answers are given as 5.28. Okay, then this can be written as 5.28 times 10 to the power minus 4, right? 5.28 times 10 to the power minus 4. What is it? 5.28 times 10 to the power minus 4. Answer 2. Right? A combination of force equilibrium with surface tension. Right? Force equilibrium with surface tension. Right? Simple as that. Only force acts on this one is force due to surface tension. Right? Force F is due to surface tension on each leg. That is how I assume. Right? Since there are 6 legs, total force is 6F. Something like that. Total force is 6F. Right? That's what I wrote at once here, 6F. Total force is 6F. Right? I will let you know again what's the date, what's the day actually that I'm going to take again for surface tension, right? I'll be taking another day for surface tension for sure, right? And for other lessons we are covering in our theory classes, right? Thermal parts, right? Optics, thermal parts. Now we are to start thermodynamics, no? For thermal parts, then elasticity, matter and radiation, right? Since we are starting matter and radiation in the following week in the reverse class, matter and radiation. So likewise, I'll be allocating sessions. So keep in touch, keep in touch. So you can get all updates through all channels, WhatsApp channel, Telegram and YouTube. Through all channels, you can get the same updates, right? Okay, next, let's move on. 15. A loop made of a string of length L is placed on a soap film. When the portion of a soap film inside the loop is broken, the tension of the string becomes T. Right? We have proved this scenario. Right? We have proved this. If a loop is made inside the soap film like this, right? Like this, we have proved an equation for this tension. What was it? What was it? Right? If this tension is F, this tension is given by 2TR. If this tension is F, this tension is given by 2TR. Right? That's coming from the theory part. That's coming from the theory. Then it says it becomes T. If the length of the string is changed to 2L, the tension of the string will be, right? Now in this equation, we don't have length of the string, but instead what we have is radius, right? This is radius. This is radius of loop, right? This one, radius of loop. And this is tension in this equation, no? This is tension. Maybe in radius. The radius we have the radius, no? And the length is given, no? Length we know how to convert a length to a radius, and basically the relationship between the length and the radius. Length is all around. When make a length is what is here. So that is circumference basically, which means L equals 2 pi r. L equals 2 pi r. Radius is given by L over 2 pi. Radius is given by L over 2 pi. Right? Now let's apply this equation for these two cases. Our equation is F equals 2TR. No? For first scenario, if I apply, it says tension of the string becomes T. Then first one, it is T. Tension is given as T. 2. Let's assume surface tension as T dash. Otherwise, you are going to mess up the T and T dash. No, we can surface tension and tension of the string. They are two different things. I assume surface tension as T dash. Right. Then 2T dash R, instead of R, we can write L over 2 phi. L over 2 phi. Right. And do the same for second scenario. If the length of the string is changed to 2L, the tension of the string will be. So let's say new tension of the string is T1. New tension of the string T1 equals 2T dash, same liquid, and L is changed to L over 2 phi. Right? Now what you can do is either you can give a substitution, right? A plug-in of values, or divide these two. Right? I will divide. Then 2T dash to 2T dash cancels. L to L cancels. Right? 2 phi to 2 phi also cancels. Then what is remaining is T over T1. Right? T over T1. T over T1 equals, from this one nothing remains, and from here only 2 remains. That's it. I need T1. Then T1 equals, cross multiply this, 2T. T1 equals 2T. The answer is 2T. Right? Easy, right? Answer is 2T. Now, as long as you know the equation, tackling this is very much easy. Right? But if you don't know the equation, then there is a fundamental mistake you have done. Equations right? You are just 25 weeks ahead of the exam. Right? Knowing equation is the fundamental requirement here. Right? Because just by knowing equations, that doesn't mean that you can tackle all questions. Equations දැනගත්තා, theory දැනගත්තා කියලා හැම ගානම හදන්න බෑනේ. Right? ඒක දන්නවනේ කොහොමද? In a subject like physics especially, right? Knowing equations doesn't mean that you can tackle all the questions. No, never. Right? Knowing equations, that's a fundamental requirement you have to have. right? Fundamentally, we have to know only equations. That's true, right? So if you can't remember equations, now you are beyond the high time, right? You are beyond the high time. So start just after this discussion itself. If you can't remember equations, right? Because if you know equations only, you can apply it in a question and try it out, right? Knowing equations කියලා කියන්නේ මෙතන තියෙන fundamental එක, right? මතක තියාගන්න. In surface tension, we don't have like more equations. We have like 5-6 equations, right? Just keep them in mind. 16, last one for the day, right? Last one for the day, because with the time and the number of questions from surface tension we had, we have means we have had in past papers. We can't do the entire thing with a single S2A discussion, because S2A sessions are usually like 1 to 1.5 hours sessions, no, right? For the ease of being in the session, right? නැත්තම් ගොඩක් class session එකේ ඉන්නකොට distractions වැඩිනේ, and the focus and the concentration is not going to work that way. No, that's why I'm doing this way, right? Around 1.5 hours, 1 to 1.5 hours sessions තමයි යන්නේ, right? All right. 16. The capillary rise of water in a glass capillary tube is H. Right. Capillary rise of water in a glass capillary tube is H. Capillary rise. ආය අපේ equation එකට යන්න. The angle of contact between water and glass is 0. Another capillary tube of the same dimensions is made of material for which the angle of contact with the water is 90. Right. The capillary rise of water in the second tube is, right. If angle of contact is given, go with our equation with the angle of contact. What is it? Capillary rise, H rho G equals 2T over capital R cos theta. 2T over capital R cos theta. Where capital R is radius of tube, right? And theta is angle of contact. Theta, angle of contact, right? And H is capillary rise. H is capillary rise. Rho and G are usual meanings, T usual meaning, right? Now apply this equation for these given scenarios. 2 scenarios given, right? First scenario and the second scenario. For first scenario, it says capital rise is H, then H rho G equals, right, 2T over capital R cos theta. Angle of contact between water and glass is 0. Then cos 0. What's the value of cos 0? Cos 0 is 1. Cos 0 is 1. Cos 0 is 1. No? Then from the first equation, occasion, this is 2T over R. Right? So let's consider it as 1. And for the second occasion, capillary rise is asked. The capillary rise of water. Okay. So let's assume that as H dash, same liquid, same rho, same G, right? 2T over capital R, same dimensions, same R, cos theta. Cos theta here is cos 90 now. Cos 90. What's the value of cos 90? Right? Cos 90 is 0. Cos 90 is 0. Cos 90 is 0 means it's done. Right? H rho G equals, right? Anything into 0 is 0, 0, which means H dash equals 0. H dash equals 0 because rho G can never be 0, right? Rho G can never be 0. They are constant values. So H dash is 0. If H dash is 0, answer is 0. Right? When an angle of contact is 90, no capillary rise. No capillary rise occurs. There's no capillary rise. H dash equals 0. Right? Okay, that's all questions I planned for today. Right? That's all I planned for today. Any questions? Now, since we have come to the end of the discussion, any questions? Or if it is clear, say it's clear if possible in the chat. If it's clear enough, or if there's any suggestions from your side for coming SQL sessions, or any lessons that you are seeking, right? So you can give your suggestions, right? Now only 5 is remaining in the live now, right? But even if you see this later also, if you need to give a suggestion, what you can do is you can add a comment and give the suggestion. You can add a comment and you can give the suggestions, right? If you are in the live, you can share your thoughts here in the live, right? All clear. Good. Right? So reminding again, listen, reminding again, we are 25 weeks ahead of the exam, right? And I'm always trying to have one S2A discussion per week, right? So this is the fifth one, not fourth, fifth. This is the fifth discussion we are doing, right? We had 5 S2A discussions during all consecutive 5 weeks, right? Last 5 weeks, we had discussions, right? So likewise in the coming weeks also, at least one per week, right? I'll be allocating at least one per week, right? If I'm available to allocate 2 S2A discussions, definitely I'll go ahead, right? So get the benefit. And you can find all these S2A discussions under a playlist as S2A in my YouTube channel, right? So if there's anyone who needs this thing about the past paper discussions and everything, right? You can share the playlist itself, right? With anyone who is going to take the advantage of, right? All right. Then if no questions, we'll wind up, right? If no questions, we'll wind up. Yes. Nothing, no? All clear. No, right. Okay then. Then if no questions, we'll wind up. So again, what I need to say is allocate your time, utilize your time, full time for the academics these days, right? Time flies quickly. Time flies, right? 25 weeks කියලා කියන්නේ පොඩි දවස් ගානක්, right? 25 weeks means that is just nothing, right? 25 into 7 is what's the value? 25 into 7, 175, ne? 175, right? We are like 175 days ahead of the exam. 175 days ahead of the exam, right? Very small time, right? So study hard, work hard, and see you again in the next class or the next S2A discussion, right? All right then. Good night and goodbye. See you.